2020, where today we'll look at problem number 1, which is about cats. I love cats. Personally, I think cats are better than dogs. I'm a cat person. Cats are cute. Who doesn't love cats, really? So I'm not gonna read all this. So we're just gonna jump straight into the scheme. And so we have hints. We've been given hints, and they say the compound A has strong and sharp band of 3300 in the wave number, and it's also monocyclic. B and F, they're also monocyclic, meaning only one ring contains only one ring. And F has a doublet at 9.8 chemical shift. So let's start. So let's start with compound 2 right here. We treat it with sodium ethoxide. So sodium ethoxide is quite a strong base. So what's going to do is it's going to grab this proton because it's next to two carbonyl groups, which its conjugate base can resonance into the carbonyl groups and give you the enolate, right? So after grabbing of the proton, sorry, I'm a bit sick, you will get your enolate, right? So here's your enolate. And then your, this alkyne looks interesting. And then what's going to happen next is an SN2 reaction. So it will just attack here, whoosh, kick out the bromine, give you A, which has 3 oxygens. And let's calculate the double bond equivalence. And they gave us the formula for every compound. That's quite generous, actually. So let's calculate the double bond equivalence. That's 13 times 2, so that's 26, plus 2, that's 28. 28 minus 18, that's 10. The dBE equals 5. So that tells us that there are 5 double bond equivalences. So 5 places where you can add hydrogens. So A, from what we got, so this is the answer sheet. You have stereochemistry? No, we don't. Okay, good. It's just going to be this compound. So that's enolate chemistry for you. Like this. There you go. So there's A. Okay, great. Did I 4 carbons added? 1, 2, 3, 4. Okay, great. Then we treat this compound with mercury 2 sulfate in acidic conditions and then heat. So what's going to do first is that the mercury 2 sulfate will hydrate your alkyne, right? That's the hydration of the alkyne. So what's going to give you is that it's going to give you this compound, right? So it's going to hydrate the alkyne, and then it's going to change this into a carboxylic acid also. And then in the second step, when we treat it with heat, it's decarboxylation, right? Because you have the carbonyls beta in position of each other, so that's alpha and beta. So that's a beta keto acid. So it can undergo decarboxylation as follows. So we will undergo decarboxylation, right? And then you will be left with this, right? And let me just redraw that real quick. Oh, wait, I need a reference. So 1, 2, right? 3, 4, 3, 4, right? And then, okay, great. So that's my B, right? But then it also tautomerizes, right? This is an enolate, so we're going to tautomerize that too. So that's going to be the product after tautomerization. So that's B. Next, we treat it with LDA and some heat. So that's going to be your classic aldol reaction. So what's going to happen here is that your LDA is quite bulky in size, right? LDA is quite big, so it's going to grab a proton that's not hindered. It's going to grab the proton that it can grab easiest. It's quite big, so it has to choose the proton that is least hindered, which is this proton or this proton, and in this case I believe it is this proton because it's less hindered. Then it's going to grab this proton, right, forming it into an enolate. So let me draw the enolate. So here's the enolate, right? I should copy for B's answer first. So this is the answer for B. This is the answer for B. Okay. Here's B. So what's going to happen next is that your enolate attacks the carbonyl right there. So it will form a what membered ring? 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. That's wait. Okay, here's the ring. That's going to be a 5-membered ring, it seems. So it will become a, it's gonna be a hard draw. So that carbonyl would be attacked. 5-membered ring, right? There you go. That's, yeah, it seems like a 5-membered ring. Did I draw something wrong? 1, 2, 3, 4. No, not. Because Nepetalactone is 6-membered ring. Maybe there's a, it's 5-membered ring. Okay, so it's already correct. Because I based off the this structure, and I thought, isn't it a 6-membered ring? But okay. All right, let's continue. So that will be this carbon. Let me try to trace the carbons real quick. It's quite complicated. Okay, I believe this is the structure. And then what's going to happen next is that this anion will just grab a proton. So proton transfer, grab proton like so. And then with another molecule of LDA, this hydrogen will be abstracted again, right? This hydrogen will be abstracted again with another molecule of LDA to get, again, your enolate anion, right? And then what's going to happen next is an elimination. So this will be eliminated to get, this is E1CB mechanism, right? Is it called E1CB? Yes. And then you will get your C. So this will be your C. This is C. So let me draw that real quick. So it's a 5-membered ring. Like this, 2, and then like this, right? 1, 2, 3, 4. Okay, right? Let me check if I drew it correctly. Yes, I did. Okay, good. Then what do we have next? So, and then we hydrogenated that bond, and then we treated with sodium methoxide again, and we also treated with benzaldehyde. That's benzaldehyde, and so we'll get D. So what's going to happen here is that your sodium methoxide will grab a proton. So which proton will be grabbed? That might be a good question. So the proton that will be grabbed, we can get some hints from this compound. And if you can see this, this alkyl, this methyl group is untouched, is left untouched. This carbon is left untouched. It's still the same as this carbon still, right? So it tells me that this proton is the one that's being grabbed. Also, if they don't give us this compound, we can say that, this proton is being grabbed because sodium methoxide is not really a big base, so we cannot really use sterics to explain. We have to use that most alkyl groups, methyl groups, or alkyl groups, whatever groups that are hydrocarbon groups, they are electron donating. They donate electrons. Could be via hyperconjugation or whatnot. So if you abstract this proton, you will have a higher, greater electron density because you have an alkyl group donating its electrons to this carbon, right? So it will be more unstable. More electrons means unstable, right? It has a more electron density. It's quite unstable. So what's going to do is it's going to make itself stable. So it's going to grab this proton. So that's good yapping. So yeah, that's same thing. Is that a base, which in this case is the ethoxide, grabs that proton, turns it into an enolate. So it's a 5-membered ring, and then an enolate for you. It's an enolate methyl group right there. And what's going to happen next is it's going to attack the benzaldehyde. So the attack on benzaldehyde will give you D, right? And don't forget to remove that oxygen from the benzaldehyde too. So that's going to be the product, right, after proton transfer. And again, that's your product, but we've been given that there's only one oxygen, so it's going to do the same thing as we did earlier, which is an E1CB mechanism. So it's going to grab the same thing. It's going to grab a proton here, right? And it's going to eliminate out the water. So that will give you this product. So that's D. So let me draw that real quick. So I'm just going to copy from C then because I'm way too lazy. So that would be this compound. So that's D. Okay, great. What do we do next? Then we treat it with sodium borohydride and acid anhydride and acetic anhydride. So what's going to do here is that it's going to, of course, sodium borohydride reduces your carbonyl, right? So it's going to reduce it here. And then we treat it with, oh, sorry about that. And then we treat it with acetic anhydride. So that's going to be a normal acyl substitution, right? So nothing really major. Okay, great. Then what's next? Then they did the ozonolysis, so that's good. So that's going to cleave this double bond. It's ozonolysis. And then they treat it with sodium hydroxide in water. And then sodium periodate. So what's... Oh, sorry. Give me a moment. Oh my god. I'm so sick. Okay, so what's going to happen right here is that the sodium hydroxide will cleave the AC group, right? The acetic group, right? It will cleave this bond, so you will be left with a normal alcohol instead. So you will be left with a normal alcohol instead. Oh my god. I hate having cold, man. Great. Then the sodium periodate will cleave this bond. It's similar to the what you call this? The diol cleavage. So there's this reaction where you have a diol, and then you use sodium periodate, you will get two aldehydes, right? In this one, it's quite similar, so it's going to cleave this bond, and you will get this compound. And you will also add the OH groups onto the bond that you cleaved also. So that's we'll like so, right? So we cleave this bond, we add the hydroxyl groups to the either end, and then this acetal kinda will of course just become an aldehyde, a carbonyl, right? So it's the same thing, it's equivalent to each other. The mechanism isn't really what I drew, but it's a shorthand, so yeah, it's you get a general idea. Okay, great, so that will be F. Okay, so that's F. F. Okay, let me draw that real quick. So 5-membered ring, methyl group, carboxylic acid, this. Great. That's F. And then G, it's in equilibrium with each other. So what's going to happen here is that your this group, this OH of the carboxylic acid, will just attack the aldehyde. So it's nothing much. It's just that. So there we go, G, which is close to what we are having. The nepetalactone, whatever. Hey, come on. Okay, that's G. Do we miss anything? We are missing a methyl group. Great. And then from G to the nepetalactone itself is just dehydration, right? Because as you can see, we have a loss of water, and calcium chloride is a sucker for water. It loves water so much. So what's going to happen here is just dehydration of that, and that's all. So that's dehydration to give you the lactone. Let me write it here. Great, and that's the scheme of this part. And then let's look at the next one, which is the reactions of this compound. So I have some drawings I made before I made this video. Okay, so let's look at the reactions. And we've been so they chose this stereoisomer. They chose this enantiomer pure version of this lactone, and then we've been given reactions and whatnot. So let's read some hints they've given us. Reaction of 1 with DDQ gives highly conjugated compound H. Also, thermal reactions on compound H with p-quinone gives I with a molar mass of 226. So they gave us the molar mass of I, that's 226. During the formation of I, a sequential pericyclic reactions and oxidation reaction takes place. A well-known gas forms during the reaction. So I is pericyclic. J has a strong band between 3300 to 2500 in the IR spectrum. So J has 3300. And how many? 2500, okay. Great. Okay, let's see. So the relation between 5 and 6. Which of the following is true? Tick the box to the correct. Oh, okay, so they're asking us the relationship between 5 and 6. So let's see. As you can see, we have only one stereocenter that is inverted. So this is still dash, 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 wedge, wedge. This is the same, right? But this one changed. Only one stereocenter changed, not all. So that's diastereomers, right? They are diastereomers. And of course, diastereomers are stereoisomers. So let me tick this also here. So they're diastereomers and they're stereoisomers. Okay, let's see H, I, and J. So we treat the Nepetalactone with DDQ. DDQ is a very strong oxidizing agent. It's really strong oxidizing agent, and it really loves to aromatize the rings. It really loves to add double bonds into rings to make it aromatic or conjugated or whatever. So we can say that H is highly conjugated, yes. So of course it's going to make a double bond here to make it conjugated, a ring, to make that ring conjugated. So it must have or add a double bond here, right? So we'll oxidize these two carbons and then add a double bond here, and it will make the ring conjugated. So H will be, oh, now I have to label the stereochemistry. So the methyl group, and then your lactone itself, that's H. There we go, that's H. Great. And let's see if I'm not missing any stereocenters. Okay, great. Let me draw this a bit more. Yeah. Okay, what next? Then we treat it with we treat it with this quinone. And then we, okay, so this is part of step 1, and 2 is just oxygen. So 2 will oxidize the product from 1. So what's going to happen here is that we've been given that it's a pericyclic reaction, so we can say that it is a Diels-Alder reaction, right? Because as you can see, we have a diene right here, and we have another a dienophile, right? This is a dienophile come into contact of each other. So what's going to happen here is that, let me draw this, and then your quinone will come into contact by forming a 6-membered ring at Diels-Alder reaction. Let me draw a dotted line to indicate the new bonds that are being formed. There you go, those are the new bonds that will be formed to give you this intermediate. Okay, it's gonna be a bit hard to draw. Okay, bear with me, just bear with me. Ooh, okay, yeah, we doing this great. Okay, so that's your intermediate. I hope you can see, I hope you can visualize it clearly. Let me try and make it a bit more clearer by adding a wedged bond over here, and a wedged bond over here also. Okay, great, so you can see it more clearly. Alright, nice. Then we have been given that a well-known gas forms during this reaction. So we can say that, hey, this looks really similar, right? This looks really familiar from what we know. And you would be right, this is carbon dioxide, right? You just eliminate this group out. You eliminate carbon dioxide out, and it's quite well known, right? So what's going to happen here is another pericyclic reaction will take place in which this double bond will move over here. This CO bond will collapse, and then this double bond will just move here. So that will be another step of pericyclic reaction to give you almost the final product of I. So you will get, let me remove that. Okay, that bond looks really elongated. Let me draw again. And you will get this compound, right? And we added oxygen. And we added oxygen. This is only after step 1, all right? And then we added oxygen, so that will oxidize something. Oxygen is an oxidizing agent. So what's going to happen here is, of course, the oxygen will aromatize that ring. It will oxidize and aromatize that ring, make a benzene, so that will give us I. And you can actually use the hints to help you out also. Now let me draw I first. I feel like this video is going to be really long. Okay, so what we can have here is that, okay, before aromatization, right, you will count the molar mass. We will calculate the molar mass. So let's see how many carbons we have. That's 14 carbons. Can we confirm that's 14 carbons? I think we can confirm that's 14 carbons. How many hydrogens do we have? Oh, we'll think about that by using the double bond equivalent. So how many double bond equivalents do we have? We have 8 double bond equivalences, right? Well, let me count again. Yeah, we have 8 double bond equivalences. So 14 times 2 plus 2, that's 30. 30 minus something over 2, that's 8. So that would be 16, right? So we have 14 hydrogens, right? We give 16. Oh. Calculate the molar mass. 12 times 14, that's how many? Shit. 156, right? And another 12, that's 168. Okay, carbon is 168 plus 14, that's how many? I hate mathematics, dude. 182 plus 2 the hydrogens, that's 16 times 2, 32. 4. Eight plus 3, that's 1, right? I think there's something wrong with my calculations. Maybe the number of hydrogens or something. Wait. So 14 carbons. Right, let me count again. Yes. And then hydrogen, how many do we have? That's 4, 5, 6, 7, 8. That's 8 double bond equivalences. Oh, did I forget to? No, I didn't. I'm just going to pull up my calculator real quick. Give me a moment. So, oh my god. So 14 times 2 plus 2, that's 30, right? 14 times 2, that's 28. 30 minus something, which is the number of hydrogens, over 2, that's equal to 8. Yeah, 14. 12 times 14 plus 14 plus 32. Am I doing something wrong? Am I missing something? I'm missing a methyl group. Oh my god, dude. I was missing a methyl group. Oh my god. That's plus. Alright, that changes everything. Alright, let's try again. So we have now 15 carbons. Oh my god. 15 carbons. 32, right? Now we have 32 minus something, which is a number of hydrogens, over 2, that's equal to 8. 16, so we have now 16 hydrogens, right? Using the calculator, 12 times 15 plus 16 plus 32, that is 228. So this compound has a molar mass of 228 grams per mole. But since we know that the molar mass of I is 226, that's a difference of 2 grams per mole, right? And that's perfect because the hydrogens right here, when we eliminate it out, we eliminated 2 hydrogens and we eliminated 2 grams per mole of molar mass. So now we have 226, and it fits right into the hint that they gave us. So that should be I. I'm so sorry for forgetting that methyl group. And And I was wondering, oh, what's wrong with my calculations? All right, whatever. We're almost there. Okay, J. So what's we're going to do with J? So starting from 1, we treat it with hydrogen platinum. So what's going to do is it's going to hydrogenate that bond. So you will be left with a saturated version. And whatever the stereochemistry is, we don't know yet. And they haven't really given us any clue about it. Treatment with hydrochloric acid will, of course, cleave that ester. Yes, okay. All right. Yes. Yes, okay. Then hydrogen and platinum. And then we have been given that J only has 2 oxygens, but here we have 3. So what does the hydrogen and platinum do? And we can use the clues that we've been given, 3300 and 2500 wave number, that corresponds to the carboxylic acid functional group. And they also say that's broad, right? It's very broad. So very broad usually means carboxylic acid. So what they've given us is that we should remove 1 oxygen out of this molecule. So we have to choose which oxygen. And since we know that 2 bands appear, which belongs to the carboxylic acid, we can just remove this out. And so we don't have to mark the stereochemistry of this carbon anymore. It's achiral now. So that's your J. So let me draw J real quick. I'm just going to copy from this one instead then. I'm just going to copy from here. And that's going to be J. Great, right? That's okay, yes. Okay, great. I mean, you can also draw a dashed hydrogen. Oh, that hydrogen is a wedge. Okay, I mean, you can also draw a dashed hydrogen down at the bottom, but I prefer to do it this way. So that's J, and that's all for the IChO 2020, IChO 52, problem 1. Yeah, thank you for watching.